We've mentioned over and over that clouds form due to rising air. Additionally, we've noted that air can rise when it is unstable. But what else can cause air to rise? It turns out there's 4 different types of atmospheric lifting. Convective uplift, orographic uplift, frontal uplift, and convergent uplift. It's definitely worth getting these 4 processes listed in your notes. We'll spend the next few minutes talking about each process separately. But together, remember, these 4 processes are the way that air is able to rise to form clouds. Our first type of atmospheric lifting is convective uplift, which is simply uplift due to convection, due to warm, unstable air rising. This is the type of uplift we've been talking about in the last video clip. The air is warmer and thus less dense than the surrounding air, so it rises spontaneously. We call that air unstable. If it rises far enough, it'll go higher than the lifting condensation level, and clouds will begin to form. So convective uplift. It's essentially simply warm, unstable air rising. Where would you expect this to occur? Well, of course, it could occur in equatorial regions that are very warm and tend to have warm, unstable air. It could also occur in the middle of the continents in the summertime when we get very warm temperatures. Thinking about California, we definitely have convective uplift that occurs in the Central Valley in the summertime when it gets so hot there. Next, orographic uplift. This is uplift of air that occurs when the air mass is forced up over a topographic barrier. When the air is forced upward, it expands and cools, and if it gets above the lifting condensation level, again, clouds will form and you'll have rain. In the case of orographic lifting, on the windward side of mountains, we tend to get a lot of rainfall. When the clouds are getting pushed up, if they get to the lifting condensation level, the clouds are forming, and perhaps rain occurs. So the windward side of mountains tends to be really wet and rainy. On the other side, the leeward side of the mountain, the air is descending and warming and drying as it goes down, and we have very dry characteristics here. We've already mentioned we call this area, the leeward side of a mountain, a rain shadow. We've previously mentioned that the Sierras gives us a good example of that. On the western slopes of the Sierras, it can be quite wet and rainy and snowy, and we have dense pine forests that result. And on the eastern side of the Sierra, in the rain shadow, we have basically a scrubland because there's not enough precipitation to support large forests. Another place that we see a rain shadow from orographic lifting is the Big Island of Hawaii. Hawaii is within the trade winds, right, between 0 and 30 degrees north latitude, where we tend to have the northeast trades. So they're getting their weather from the north or the northeast. On the windward side of the island here, the Hilo side, they get about 128 inches of rain a year. It's a virtual rainforest. Then as the air is pushed up over the mountains, which happen to be volcanoes here on the Big Island of Hawaii, the air cools adiabatically, reaches its dew point temperature, condensation occurs, and you have a lot of rainfall. On the other side, however, as the air comes down, it warms and dries, and you have a virtual desert on this side of the Big Island. Look at Kona. Kona only gets about 10 inches of rain a year. As the crow flies, Hilo and Kona are not very far apart from each other, and it really only takes you a few hours to drive from one to another. Yet Hilo gets over 10 times as much rain as Kona due to the topographic barrier and the rain shadow effect. So where do we find orographic lifting? Anywhere we have topographic barriers. The third type of lifting is called frontal uplift. This is uplift that occurs when a warm air mass and a cool air mass meet. A front in meteorology is when warm air and cool air come together. So in this case, when a warm air and a cool air mass meet, the warm air is pushed up. The warm air is less dense, and so the cool air slips underneath it, pushing the warm air up. Of course, as the warm air moves up, it cools adiabatically, and perhaps it cools to the dew point temperature, 100% relative humidity, and clouds may form and rain may fall. This type of uplift is really common in the mid-latitudes, where we have a mixing of cool and warm air. Our final type of uplift is called convergent uplift, and this is uplift that occurs when two similar air masses, generally warm air, meet. And basically they come together and they have to go somewhere, so some of the air is forced upward. This is most common in the intertropical convergence zone near the equator, where we have the convergence of the northeast and southeast trades meeting at the equator, and some of that warm air is pushed upward. So the equatorial regions tend to have both convergent uplift and convective uplift. And if there happen to be mountains in the area, they might have orographic uplift as well. Now that we understand the 4 different types of uplift, all of which can cause air to rise, cool adiabatically, and create clouds and potentially rain, let's try to analyze a particular situation. Here's an isohyot map of Nevada, essentially a map showing the rainfall distribution. The darker areas get more than 16 inches of rain, and then you can see as the colors get lighter, that means less and less rainfall. So you'll notice in Nevada the rainfall patterns are not random at all. There's a linear pattern to them. What's going on with that? Why do we have this linear pattern of rainfall? Any ideas? Well, let's look at a shaded relief map of Nevada as well. Here we can get an idea of the topography of the state, and we can see all of these strange linear-looking mountains that run north and south throughout the state. In a few weeks, we're actually going to learn about why these linear mountain ranges exist in Nevada, but for now, let's just keep that on the back burner. What we do recognize now is that the rainfall patterns are directly related to the topography. What we have essentially is a bunch of rain shadows, a bunch of windward side of the mountains where they're getting a lot of rainfall, and then the leeward side is getting not much rainfall at all, a rain shadow. So we see that situation repeat itself all throughout the map. So this is a great example of orographic lifting and the rain shadows that result. In California, we see the same scenario. We have rain shadows on the leeward side of mountains, both in the Coast Range and then again in the Sierras. All right, that pretty much covers it for atmospheric uplift. I encourage you to pause the video and answer these 3 questions in writing or at least verbally to yourself. You'll be glad you did.